Hello and Assalamu alaikum wa rahmatullah wa barakatuh and good evening. So we would like to present our group project of our course name Process Control System, and that is prepared by our group members, which is Muhammad TK, Miklid, me. Secondly, Aziz Hazan. Thirdly is Bashar Ali. Let's go to the intro and take a overview about our project. So the thing that we would like to discuss it in this intro, the crush temperature control, also the BID tuning method, classical techniques, example of application that use BID controller. Let's go more about the objective that required in this project. So the objective of this project to develop a controller for heating process and fulfill the desired performance as requested. Firstly, we need designed BID and robust BID controller. Secondly, percentage overshoot of less than 6%, settling time of less than 1650 seconds, steady state error of MSE less than 1.5 multiplied 10 power of 4. Let's see here the literature review summary, what is discussed about it. Firstly, in the literature review, talking about controller overview, BID controller overview, advantage of BID controller, application of BID controller, also the implementation issues of BID controller. There is issue while we implement the BID controller, and while we implement, we use something called or another type of controller called robust BID controller to fix the issue and improving the performance in complex system. So let's see the implementation issue of BID. Controller face challenge with the nonlinear and time varying system, making tuning time consuming and ad hoc. However, robust, as just now I mentioned, robust BID controller addresses these issues to improve the performance in complex system. And that's all for me, and I will pass to the next part to my friend. Thank you.
Assalamu alaikum and good day. Here is Bashar Mustafa Ali Muhammad Ahmed, matric AA200076. I'm going to present for the methodology and the calculation. So firstly, for the methodology of our project, first we need to find the parameters, which is K and tau and theta. Then we measure the error. Then we need to derive the system transfer function, which is using the FOBTT. And then we measure the error, and then we design the BID controller, which is using the Ziegler Nicholas. And then the error, we check the error, and then we find the transient and steady state analysis of the BID controller, and then we check the error. So next, for the calculation, firstly, here is the system response graph. And first we need to find the system scale for X and Y. And for X, it is time in seconds, and for Y is the temperature in Celsius. And here is the measurement for each millimeter. We have 2.78 Celsius, and here we have for each millimeter we have 25 seconds. So first, we need to find the S, which is the whole system response. We find as 230.58 Celsius. And then we find the M, which is the initial condition, which is 27. And for the A, which is from the initial condition to the S, which is 203.58 Celsius. And for the B, which is 5 volt. And the theta, which is the delay, is 175 seconds, which is from here. Then we calculate for the tau. First, we need to measure 63.2% of system, the A, this one, which is plus the initial condition. So after we find the tau, which is 1350 seconds, we can calculate the K, which is the gain. So, which is A over B, 40.72. Then we do the transfer function of the system. We just substitute the parameters we get here, which is the K, the gain, and the tau, and the theta here. So now we need to design the PID controller, which is using the Ziegler-Nicholas. We need to do the calculation first. And from the table, we can calculate the KB and the TI and the TD. For the PID, first we calculate the KP, which is 1.2 over tau, 1.2 multiplied tau over K theta. So we find 0.227. Then for the TI, which is 2 multiplied with theta, so 2 multiplied 175, we get 350 seconds. And for the TD, we multiply 0.5 multiplied by theta, so can get 87.5 seconds. Now we need to find the KI. KI is the KB over the TIs. We already found the KB and the TI, so we just divide them, and then we get the KI. Then for the KD, after we find the TD and the KB, we can find the KD, which is 19.88875 S. So now, since the system requires track constant, we need to find the track constant, which is by taking the square root and we multiply the TI and the TD here. So we get 0.005714. So as we see here, here's the block diagram of the system, which is the Ziegler-Nicholas PID controller. And here is when the PID back calculation until the wind up. So here is the block diagram of the system. So that's all for my part. Thank you.
Assalamu alaikum. My name is Aziz Hazan, okay, from Group 2. This is our PCS project. Okay, so I'll be handling the results and analysis. Okay, so we designed two PID controllers, which is the Ziegler-Nichols PID and the robust PID. So we analyzed both controllers using the steady state and transient analysis. Okay, so with me here on the page, figure 4.7 shows the response from the Ziegler-Nichols PID, which was run for 8,000 seconds with a set point of 150, and it is the overshoot can be seen as shown in the diagram. And then for the robust PID in figure 8, you can see the set point as well. It was run for 8,000 seconds as well, and the overshoot is shown. So the difference between this response is the overshoot and then their transient analysis generally, okay? But it is obvious from here that Ziegler-Nichols PID has a higher overshoot than the robust PID, meaning that the robust PID performed better than the Ziegler-Nichols PID. So from the transient analysis shown here, we can see the percentage overshoot for the ZN PID is 40.25, and then for the robust PID it is 3.5931. So the robust PID outperformed the Ziegler-Nichols PID in terms of overshoot. And as regards the settling time as well, the robust PID was able to perform better too. It has a lesser settling time than the Ziegler-Nichols PID by almost half. Okay, so for the steady state analysis, we use the mean square error analysis. Okay, so here is the comparison between both controllers, Ziegler-Nichols and the robust PID. So Ziegler-Nichols PID is the response at with the purple color, the purple ink, and then the robust PID is with the green ink, and the set point with the red line. So we can see that the overshoot reduced greatly, right? Okay, so from the mean square error, according to the requirements, the mean square error should not be less than 1.5 to the power of -4. Okay, so after designing the controller, it was deduced that the Ziegler-Nichols PID couldn't beat the company's requirement. However, the robust PID was able to beat the company's requirement. Okay, so for the mean square error analysis of the robust PID, it was 0, and the Ziegler-Nichols PID was around 7.9 to the power of -3. And then I'll move to the simulation. Okay, so according to the PID designed using MATLAB, the PID was actually designed using MATLAB. I haven't calculated our parameters and everything. So here is the PID designed for 8 seconds that we use and run it. So I'm going to run this to show you the response, okay, from earlier. So now I have clicked on run, and it's going to take a while for it to run. Okay, so here are the gain parameters. Here is the set point, the saturation, our transfer function of the plant. Here is the time delay, and this constant here is the initial condition. Okay, so as you can see, the PID has run from the scope. As you can see here, this is the response of the Ziegler-Nichols PID. Okay, here is the time delay, and then here is the percentage overshoot, and from here the settling time was calculated. Okay, so moving on to the robust PID, the PID with back calculation and wind up here. Okay, so it is actually derived from Ziegler-Nichols PID. It's just that the time tracking constant was added to it, and then I think that is just it. The time constant TA. That is actually the main difference between the Ziegler-Nichols and the robust PID. So here is the transfer function, saturation, the time delay, and then the initial condition as requested by the company. Okay, so I'm going to run this to show you the response. So it has run, and as we can see here, here's the response of the robust PID. So the robust PID was able to outperform the Ziegler-Nichols PID and was able to beat the requirement of Ziegler-Nichols PID. Okay, so if there is one, if there are drawbacks of the Ziegler-Nichols PID, the robust PID was created to fill in the defect. The imperfections of the Ziegler-Nichols PID. So therefore, the project was successful, and we were able to design a robust PID to meet the company's requirements in terms of the overshoots and the settling time, as well as their mean square error, which can be summarized as the transient and the steady state analysis. So that will be all from me. Thank you.